Welcome to SS2 Physics, Term 3, Week 7. One of the most profound discoveries of 20th century physics is that light and matter simultaneously exhibit both wave-like and particle-like behavior, a phenomenon called wave-particle duality. This challenged the classical physics worldview and gave birth to quantum mechanics. By the end of this lesson, you will explain the photoelectric effect as evidence for the particle nature of light, define the photon, state Planck's equation, describe electron diffraction as evidence for the wave nature of matter, explain de Broglie's hypothesis, and answer WAEC questions on this topic. Let us begin. The photoelectric effect: when light of sufficient frequency is shown on a metal surface, electrons are emitted from the surface. These emitted electrons are called photoelectrons. Observations that classical wave theory could not explain. Effect 1. Threshold frequency. Electrons are only emitted if the light frequency exceeds a certain minimum value called the threshold frequency, F0, specific to the metal. Below F0, no electrons are emitted, no matter how intense the light. Classical wave theory predicted that enough energy should eventually arrive to emit electrons regardless of frequency. This was not observed. Effect 2. Kinetic energy depends on frequency, not intensity. The maximum kinetic energy of emitted electrons depends on the frequency of light, not its intensity. Increasing intensity increases the number of electrons emitted but not their kinetic energy. Effect 3. Instantaneous emission. Electrons are emitted essentially instantaneously even at very low light intensities. Classical theory predicted a time delay for enough wave energy to build up. Einstein's explanation, 1905, one of his Nobel Prize-winning papers. Light consists of discrete packets of energy called photons. Energy of one photon, E equals hf equals hc lambda, where h equals Planck's constant equals 6.626 times 10 to 34 J/s, f equals frequency, hertz, c equals speed of light equals 3 times 10 meter per second, lambda equals wavelength, m. One photon interacts with one electron. It either has enough energy to free the electron or it does not. Work function, phi, the minimum energy needed to remove an electron from the metal surface. Phi equals hf0, where f0 is the threshold frequency. Energy equation, a photoelectric effect. Hf equals phi plus Ekin, max, where Ekin, max, equals maximum kinetic energy of emitted electron equals 1/2 mv superscript 2 max. Rearranging, Ekin, max, equals hf, phi equals hf, f0. This is a linear relationship between Ekin, max, and frequency, verified experimentally by Millikan in 1916. If light, classically a wave, has particle properties, photons, do particles, classically thought to be points with definite position and momentum, have wave properties. De Broglie's hypothesis, 1924. All matter has an associated wavelength, the de Broglie wavelength, given by lambda equals h/p equals h/mv, where lambda equals de Broglie wavelength, m, h equals Planck's constant equals 6.626 times 10 to 34 J/s, p equals momentum, kg, m/s, equals m times v, m equals mass, kg, v equals velocity, meter per second. For large, slow-moving objects, like a cricket ball, lambda is incredibly small, far too small to observe wave effects. For electrons, very small mass wavelengths can be comparable to atomic spacings in crystals. Wave effects are observable. Evidence for electron waves. Electron diffraction experiments, Davison and Jama, 1927. Electrons fired at a crystal of NECO produced diffraction patterns identical to X-ray diffraction, proving electrons behave as waves when interacting with the crystal lattice. The diffraction pattern depends on the wavelength of the electrons, controlled by their accelerating voltage, and the spacing of atoms in the crystal. Modern applications of electron diffraction, electron microscopy, TEM, SEM. Because electrons have much shorter wavelengths than visible light, they can image details far smaller than optical microscopes, resolution limit of about 0.1 nanometers, much smaller than 200 nanometers for optical. De Broglie wavelength calculation example, An electron accelerated through 100 V has kinetic energy E equals EV equals 1.6 times 10 minus 19 times 100 is equal to 1.6 times 10 to 17 J. P equals square root 2 m equals square root 2 times 9.11 times 10 to 31 times 1.6 times 10 to 17 equals square root 2.916 times 10 to 47 equals 1.71 times 10 to 23.5, approximately 1.71 times 10 to 23 kg/s. Lambda equals h/p equals 6.626 times 10 minus 34 divided by 1.71 times 10 minus 23 almost equals 3.87 times 10 to 11 m equals 0.039 nanometers. This wavelength is comparable to atomic spacings, 0.1 to 0.3 nanometers. Conforming electrons can diffract off crystal lattices. Wave-particle duality summarized. Light behaves as a wave in interference and diffraction experiments. Young's double-slit diffraction gratings. Light behaves as a particle in the photoelectric effect. It delivers energy in discrete photon packets of E equals hf electrons, and all matter behave as particles in most everyday contexts. Electrons, and all matter, behave as waves in diffraction experiments, with the Bohr wavelength lambda equals h/p. The principle of complementarity. Niels Bohr wave and particle descriptions are complementary. You cannot observe both simultaneously in the same experiment. In diffraction experiments, you observe wave behavior. In photoelectric experiments, you observe particle behavior. Heisenberg's uncertainty principle, 1927. It is fundamentally impossible to know both the exact position and exact momentum of a particle simultaneously. Delta x times delta p greater than or equal to h/4 pi, where delta x equals uncertainty in position, delta p equals uncertainty in momentum. This is not due to poor instruments, it is a fundamental feature of quantum objects. It arises from wave-particle duality. To localize a particle in space, determine position, we must use short wavelength radiation, which has high momentum, high energy photons, disturbing the particle's momentum. This principle is not covered in detail in WAEC SS2, but students should be aware of it. Planck's quantum hypothesis. 1900. Max Planck proposed that energy is emitted or absorbed only in discrete amounts, quanta equals nhf, where n is an integer. This was the birth of quantum theory. Worked example 1. Light of frequency 8 times 10 superscript 1 Hz is shown on a metal with work function 3.1 electron volts. H equals 6.626 times 10 to 34 J/s, 1 electron volt equals 1.6 times 10 to 19 J. A. Calculate the energy of 1 photon in eV. E equals hf equals 6.626 times 10 to 34 times 8 times 10 superscript 1 equals 5.30 times 10 to 19 J equals 5.30 times 10 minus 19 divided by 1.6 times 10 minus 19 is equal to 3.31 eV. B. Is the photoelectric effect observed? Yes, photon energy, 3.31 electron volts, exceeds work function, 3.1 electron volts. C. Calculate maximum kinetic energy of photoelectrons. Ekin, max, equals hf, phi equals 3.31, 3.10 is equal to 0.21 eV equals 0.21 times 1.6 times 10 minus 19 is equal to 3.36 times 10 to 20 J. Worked example 2. Calculate the de Broglie wavelength of an electron, m equals 9.11 times 10 to 31 kilograms, moving at 2 times 10 meter per second. Lambda equals h/mv equals 6.626 times 10 to 34 9.11 times 10 to 31 times 2 times 10 equals 6.626 times 10 minus 34 divided by 1.822 times 10 minus 24 is equal to 3.64 times 10 to 10 m equals 0.364 nanometers. WAEC questions. State 2 observations in photoelectric effect that wave theory could not explain. State Einstein's equation for the photoelectric effect. Calculate photon energy from frequency or wavelength. State de Broglie's hypothesis. Calculate de Broglie wavelength for an electron. Key points. Photoelectric effect demonstrates particle nature of light. light consists of photons with E equals hf threshold frequency f0, minimum frequency for electron emission, phi equals hf0, work function. Einstein equation, hf equals phi plus Ekin, max. Increasing intensity more electrons, not more energy per electron. Increasing frequency more kinetic energy per electron. Wave nature of matter, de Broglie wavelength lambda equals h/p equals h/mv. All matter has a de Broglie wavelength, only significant for very small, fast particles. Electron diffraction, Davison and Jama, confirmed wave nature of electrons. Wave-particle duality, both light and matter show wave and particle behavior in appropriate experiments. Key constants, h equals 6.626 times 10 to 34 J/s, Planck's constant, 1 electron volt equals 1.6 times 10 to 19 J, WAEC mainly test, photoelectric effect calculations, E equals hf, Ekin equals hf, phi, de Broglie wavelength, lambda equals h/mv, qualitative understanding of duality.